thing about internet provision, it's a pyramid, and at the top are what we call the tier 1 backbones, right? These are big telco companies nationwide. Let's just talk transcontinental, fiber optic backbones, very high speed, right? That's as good as it gets. So if your internet provider offers a tier 1 connect, you're up at the top, and since you're up at the top, you have a more direct path to a high-speed internet provision. As you go to the lower end of the scale, again, the mom and pops, most of the mom and pops aren't going to offer you a direct connection to tier 1, right? So they probably offer you a connection that goes through them and another provider, and maybe even another provider before you get to the tier 1, right? This is performance affecting because what you're going to see in the course of this talk is every device that's between you and the Testi server is going to add latency. And as latency increases, your performance decreases. Does that make sense? It's just time. Now all we're talking about, ultimately, since we're talking about workflows, is an IP packet that goes from your workstation to Cheyenne, right? Under the current model, though, you're using the public internet to get there. And as we're agreeing now I hope, these providers have their own networks that have a bunch of devices in them that maybe talk to another provider that has a bunch of devices, routers, switches, firewalls, that maybe talk to another provider that has the same thing. And every time your little packet goes through one of those devices, it takes time. As the time it takes to go through there increases, your human measured response time on this workflow's client is going to get larger. So you're going to be convinced, I hope, that some of the performance degradation, variation in performance that you see is not necessarily that something's broken, although it could be, but it's more aptly to be related to the fact that there's load somewhere on the net. Now, can we go back to the original premise that probably internet access at 2 in the morning is going to seem faster than at 3 in the afternoon? Why is that? Load. Load maps onto latency. As the load gets bigger, latency between the sender and receiver grows. Do we all agree on that? Mm-hmm. Excellent. Right. So you can probably find yourself or your workstation on this general schematic. For instance, here's a workflow client with the local area network it goes through. Call that your county library in your building network. That talks to a piece of demarcation equipment owned by the service provider. Let's say it's a DSL modem, which takes you into the first network after yours that you have to transfer, and that's the provider network. And then inside that provider network is a list of services that the provider does for you. So does this kind of look familiar as a customer? Do you see yourself here? All right, now this one's a little bit more blown up in detail to look a little bit closer. Here's your switch. Here's the provider demarc equipment. It may be a router, we don't know. But then you get into your local providers, this is world, and this is probably your local, in a lot of cases, your local telephone central office, right? And then you get firewall that's doing firewalling for you under your contract. And then that hits a router. And that router plugs into another segment. Here's, for instance, could be an email server that's holding your email service, your mailboxes. Here's a DNS server that's resolving names. And here's another router that goes, hopefully, on a tier 1 connect to this thing called the public internet, which is a whole nother set of all these entities, right? And ultimately, you may go through another one of these to get where you're going. Now, there's 2 types of delay that we care about. One is physical delay. In physics, it takes bits enter a wire or a piece of fiber optic at speed of light. They travel at the speed of light. For a reference point, a geosync satellite, 22,300 feet above the Earth, it takes about just in the order of a half a second for a bit to go up there and back, right? Over 22,000 miles, right? Now, conversely, Cheyenne's what from here? A couple hundred, 300 miles. Is there physical latency? Sure. We're in the universe. There's physical latency. But it's relatively small compared to the latencies that are added by these devices. Do we care about it? Yes. Is it really relevant in the overall latency calculation, not for these purposes. We're not forgetting about it, but when you compare it to these other devices, it's small. So this is the whole premise we're working on, is how long it takes a packet from there to get to there. How long it takes is all based on what happens to it in its travels. With me so far? All right, so why do we care about latency? Well, as we already discussed, it's delay. And I bet you can intuitively agree with me that if you're used to seeing response time that's based on a 20 millisecond round trip, and all of a sudden that response time goes to 300 milliseconds, we're still only talking about thousandths of a second, but you'll notice that, right? So latency is important. So what are the sources? We talked about that. The physics of the wire and the latency through devices. Fine. Well, what can we control? Well, speed of light's out of the question, unless you know something I don't know. So the only thing we can really control is what else happens in the path. Now, will you intuitively agree with me that a path that has 100 routers in it probably is going to have more latency than a path that has 2? Would you agree with that? And you'll feel that on your workstation. You definitely will. So can we control that? You can't control what happens in your provider world, but you may control that in your own network, because the number of devices that your packet has to traverse in your own network also adds latency. So if you have kind of an historic network that where several people over generations have worked on it, and it's kind of messy, and you don't have a brand new cooling facility, you might want to revisit your networking configuration and get lean and mean, as we say. There may be devices in there that you don't need anymore. Get rid of them, because anytime your little miserable internet packet has to go through that device, it's costing you time. The more devices there are, the more time it costs you. So where can we control latencies? In your own network configurations, and by minimizing the path. Now, what we all hope is that our providers do the same thing, right? Because the longer their path is, it will affect you as well. So we're hoping that not only you, but all your providers that you pay your monthly check to also practice this idea of efficiency in the number of devices. So what we're going to talk about is the nature of this latency. I just put this back up so you could ground yourself again on the path we're talking about. All right. Where are the main sources of latencies? Well, it starts with your client workstation, because that's the origin of your IP packet. Your packet that represents a request for a task, workflows task or something like that. Then the next source of latencies are going to be found in the number of devices that you have in your local area network. Again, with the premise that the more things that have to look at your packet, handle your packet, the more the delay will be, the more performance affecting it will be. So then you move out of your building, and where do you go next? RT, ACT, Quest, you're in their world now, right? And then you move out of that wide area network, and you may go to a whole other provider, or you may finally make it to the internet, and then you come off what we're calling the public internet, and you go through this whole scenario again, so that the wide area is not only to your direct provider, but it's everybody that your direct provider talks to as well. That's the source of this latency. And finally, once you've survived all that, and your packet magically pops out in Cheyenne and gets to the Cersei server has its own latencies. For instance, did you ever wonder why the Cersei server can have so many open connections at the same time? Well, it's keeping track and maintaining and servicing all those connections virtually at the same time. That's another source of latency, as we'll see. So let's develop these a little bit further. All right, this is the one I've repeated several times. I'm sorry these are so small. I'm excusing myself from any liabilities for your eyesight, but I want you to actually draw on these. But this is pretty much what it looks like. I've cleaned some of this up, but here's you, or here's you, and here's your local provider, or here's your local provider, and with some sort of connected internet that we talked about, and ultimately you magically pop out your packet, so to speak, onto the state network. And actually I cleaned this up because there's yet one more provider here, and there's yet one more provider here, but for simplicity,